Welcome to Open Conversation with Gideon Jacobs.
Hi, I'm Gideon. My mission is to have conversations around burning topics that is really relevant today and in the future. Some of them might be really controversial, but I hope by laying it out, we could actually have a conversation which will allow us to address these issues. My background is science and engineering, and I might bore you a little bit with some maths and science at times, but I'll try and keep it as simple as possible.
Today I would like to discuss why current renewables alone will not solve the problem. The whole debate around climate change is very hot in the news at the minute. But what is happening? Are we the cause? Can we do something? So what I have here for you is a representation which shows us the world population in relation to energy use. So the blue disk represents the global population at the year 1999. Next one is at 2019, and then we go on to a projection for 2049. At the back, there's a red disk, which is the global energy consumption at 1999. You will see that the red disk and the blue disk is the same size. So the area or the total has been normalized to the population so that we can express the global energy consumption as a ratio to the global population. So again, the red one 2019, and then we go a projection to 2049. Okay, so let's have a look. If we look at these in a plan view, then there's a couple of things that you will notice. So let's look at the total energy consumption. In 1999 was 106,533 terawatt hours for a population, a global population of 6.064 billion people. From 1999 to 2019, population increased to 7.713 billion people, and our energy consumption increased to approximately 165,000 terawatt hours. Now, if we do a projection forward based on data and a lot of research that's been done, which I will share with you in a minute, it is anticipated that around about 2049, Earth's population will reach about 10 billion people. But what is alarming is calculations that I've done projects that we're going to reach in the order of 400,000 terawatt hours in our energy consumption. So looking at the blue line here, that's linear. So we sort of have a linear growth. If you plot the population on a standard axis graph, XY axis, then you actually have an exponential increase in population. But what is alarming is the red line. So you'll see that it has a much higher exponential growth. Just to the reason why I presented it this way is using the area allows you to have sort of a bit of a linear representation of Earth's population. Then obviously we see an exponential growth in population due to the square, the exponent there. So it's the diameter divided by 2 to the power of 2 times pi. So I've expressed the population as a circle. Now what is, as I said before, really alarming is when we look at the area for the red, which is the energy consumption, which now becomes quite large. Then we see that we don't have a energy consumption that grows in proportion with the population. And the reason for that is we have become a much more energy intensive society. What we also see as cause of that is world population, and especially in the developing nations and emerging economies, which is starting to some level, start catching up with what was traditionally viewed as the first world or the West. So based on the numbers here, the 400,000 terawatt hours and the 10 billion people, the average energy consumption is going to stabilize around about the 40 megawatt hour per capita per annum. Now, the reason why I've actually came to the 400,000 terawatt hours, which I've calculated, is based on my prediction that mature economies stabilizes around about the 40 megawatt hour per capita at the moment. So, as I said before, we've got this huge tendency of these two, the blue and the red line, departing from one another. And I'm now going to first deal with showing you why I'm saying it and where and how I derived my data. So what we're looking at here is, this is the energy use per capita, thanks to a website called ourworldindata.com or .org. They have done a terrific job in accumulating and presenting information in a very useful format. So what we see here is plots since 1960 till about 2015 of the general energy consumption of various countries. So you can see that America has an extremely high energy average consumption per capita, and then over the last, since the 1970s, that has been driven down and is sitting around about 80,000 kilowatt hours or 80 megawatt hour per capita per annum. Now, if we look at the more mature economies, where you have smaller areas in terms of geographic surface area, countries like Japan and the United Kingdom obviously have less distance to travel, and they have been able to actually drive their energy consumption down to around about the 40,000 kilowatt hour mark. I want to draw your attention to South Korea, which is this light blue line here. You can see that Japan followed the same trend when they had their economy emerging, and South Korea has started in the mid-80s and is doing the same thing, and is probably going to plateau off quite soon and then start dropping back down. But what is really alarming, and there's absolutely nothing we can do about it, because emerging countries like India and Pakistan and sections of Africa, or the whole of Africa and sections of South America, they all strive to have the quality of life we have had for over 100 years in the first world, or mainly the Western world. And these economies are emerging. So if we look at India, so China again, you can see that by around about 2000, their energy use per capita has started to increase dramatically. But what is probably the most important one to look at is India, the yellow one. They have not reached the point of real turning. And if we move on to the next slide, then you can see some values of the actual energy consumption per capita in 2014. So the United States was sitting around about the 80.9 megawatt hour, Norway 65, Australia 62, South Korea 61.5. And then if we go right down to where India and Pakistan and Egypt and Brazil, those countries that have very strong emerging economies, they're sitting at Pakistan 5.6, India 7.4, and Egypt 9.4. So if we look at the world population, you'll see here that luckily we're not heading for a unstoppable exponential growth, but it's going to start plateauing off around about 2100, 11 billion mark. So 2050, they anticipate approximately 9.7 billion. For calculation purposes, I just simplified it to roughly about 10 billion. So if we look at the population, then this is where the alarming bit really comes in, is India, which is the light blue curve over here. You can see that round about, I think that's about 2023, India will surpass China in population, just as China reaches its peak. But then you have other emerging countries like Nigeria, which will experience a massive population growth, Ethiopia, Bangladesh. But China and India is probably the main ones, and then the continent of Africa. So using 2019, so we're looking at China at 1.43 billion, India at 1.37 billion, and a country like Nigeria, which is sitting at 200.96 million. Now, if we compare that with the projections for 2049, we'll see that, again, India is experiencing a significant increase, so is China, and then Nigeria is going to pretty much almost double from 200 million to close to 400 million. So, and you'll see that trend throughout Africa, maybe lesser in some countries, which is smaller, but still significant increases. So for the various continents, we're looking at Asia, Africa. You can see Africa is going to have a very steep incline. In order to get an idea of the continents, I've left India in here and I've given Russia and Europe. Asia is going to, experience a massive increase. Africa is going to experience a massive increase. India's data is included in the Asian graph up there. Mature economies like Europe, Russia, you'll start seeing a decline in population. So if we look at that, then we will see 2019 Asia is around 4.6 billion, Africa 1.3 billion, and Europe 747 million. Now if we compare that to 2049, Asia is set to reach a peak of 5.28 billion, Africa 2.45 billion, and Europe would have seen a slight decline. So let's just jump back to the energy use per capita. So based on those populations, you can see that the trend for all emerging economies are to experience a drastic increase. India is down there, and Nigeria is not on this curve, but you will see the same trends that will occur, which means that prediction-wise, I would say that we would reach at 2050 around about a global average of about 40,000 kilowatt hour per capita. So this energy is not just inclusive of a person or a household's energy use. It also takes into account industry, transportation, and all the rest of it. So let's have a look at some solar panels. Here's a bit of information that I've pulled from the internet, from a website called solarcalculator.com.au, where they help you to actually calculate your size and your roof area based on the solar panels. So current technology provides solar panels for between 250 watt to 330 watt per panel, size 1 meter by approximately 1.7 meters, which relates to if you use 250 watt panels, approximately 22, and that will result in about 34 square meters requirement. Now I'm just drawing your attention to the figure of 5 kilowatt here. If you want to have consistent output at round about the 5 kilowatt, your system should actually be round about 6.6 kilowatts. So let's have a look at the daily average production, again from the same website, solarcalculator.com.au. We'll look at, in say a region, Brisbane, Australia, which has a fairly high radiative index, and a 5 kilowatt system will produce around about 21 kilowatt hours per day. So it's time for a little bit of maths. So if we look at the average daily output, that's 21 kilowatt hours for a 5 kilowatt system, and the area is about 34 square meters. Then based on one panel being 1 meter by 1.7 meters, and you have 20 panels, gives you 34 square meters. So, but to get closer to the 5 kilowatt consistent output, one needs to have a system about 1.32, the maximum peak rated value, which is about a 6.6 kilowatts. So that, once you calculate that, it gives you an estimation of about 45 square meters per 5 kilowatts. So let's assume we have a sunshine for 365 days, which obviously won't happen, but let's assume we do, just for ease of calculations. That means we will get 21 kilowatt hours times 365 days, which relates to 7,665 kilowatt hours per year of energy from such a system. So how many systems will we need to generate what I predict to be the 400,000 terawatt hours globally required? So 400,000 terawatt hours is 400 times 10 to the power of 15 watt hours, which means it's 400 with another 15 zeros behind it. So it's a bloody big number. So we said that the system comprising 250 watt panels will deliver about 7,665 kilowatt hours, thus 7.665 times 10 to the power of 6 watt hours. So if we want to now calculate the number of systems, N, then we will need to divide the 400,000 terawatt hours by 7,665 kilowatt hours, which gives us, now hold on to your seats, a figure of 52 billion 185 million 257,665 systems. Now that is an astronomical amount. And remember that these 52 billion systems will each take up approximately 45 square meters. So how much space do we need for these solar photovoltaic systems? So we'd simply calculate it by multiplying the 52 billion by 45 square meters, and that gives us 2,348,336,594,911.9 square meters. So that is approximately 2.348 times 10 to the power of 9 square kilometers. So this is 2,348 million square kilometers. So let's say by 2050 we've tripled the efficiency of these panels, so we only need a third of that area. Thus 2,348 million square kilometers divided by 3 equals the required area of 782.8 million. So how big is that? Let's try and figure out, is it size of New Zealand, or, how many rooftops do we have to cover with photovoltaic panels to cover that amount of area? Let's figure it out. Let's see. Now, Russia is the largest country in surface area on Earth. So I've got a little picture from Google Earth here, and I've highlighted Russia all around to give you an idea where it sits and what size it is. So its size is 17.1 million square kilometers. What does that mean? Let's think about this for a second. That means in order to cover 782.8 million square kilometers, we need to cover surface with photovoltaic panels that is 3 times more efficient than current technology, 45 times the size of Russia. Let that sink in. 45 Russias covered in solar photovoltaic panels, which are 3 times more efficient than current technology. Let me put some technology in perspective. So I'm going to show you a scaled representation. So if this is a little mid-size family car, then if you run that family car for 24 hours, it consumes some petrol, and some energy is converted, which is turned into useful work by driving around. But the amount of energy that is converted to useful work is approximately 1,200 kilowatt hours. Remember, that's in 24 hours. So if you want to have a photovoltaic panel array that gives you the same output, you will need 3 arrays, which each will deliver 400 kilowatt hours. If you consider 8 hours per day that you could potentially capture sunlight, to give you 1,200 kilowatt hours. So the array size of the panel will be roughly the size of your local shopping center's car park. That's massive, comparing to what that car is in terms of its energy density and the size it takes up and its volume it occupies. Oh gee whiz, what now? Well, clearly we will not be able to service the projected energy needs with current technology renewables alone. If emerging economies have no choice but to rely on fossil fuels, the consequences will simply be disastrous. We can't stop it. We can't stop their emerging and lifting the way of life of their people. So we urgently need to find alternative high-density, zero-emissions technology. But currently there isn't any. Is there any hope? Yes, luckily there is. Now, it is time for me to utter a swear word. Cold fusion. Now, some of you might have heard this word before. Hang on, wasn't it debunked like, I don't know, 30 years ago? No, actually, it wasn't. You might be surprised, but it actually wasn't. A number of scientists continue to work on this, what I call the orphan of science, and today the evidence of it being real is overwhelming and actually accepted. Unfortunately, and when I say accepted, I mean in mainstream science, the unfortunate thing is a lot of scientists doesn't know about it, and only if you've actually tried to keep up with the research in that field will you know any different. So, to a large extent, the bulk of mainstream science is still ignoring it, regardless of the credible evidence presented. Today it is known as LNR, or low energy nuclear reactions. So LNR, what is it? LNR is a process whereby isotopes of hydrogen are fused together, resulting in a release of large quantities of heat. The beauty of it is that it has no dangerous radiation or any radioactive waste. It has been confirmed and replicated in respectable laboratories all across the world. And I'll present some evidence in a minute. But it has the potential to solve not only our emissions issue and, our carbon emissions and pollutants, which is harming the environment, but it will have the energy density to fuel the growth of these emerging economies. It could easily solve the 400,000 terawatt hour problem. So you would go, yes, okay, you're talking a lot of nonsense, so how about some evidence? So here I go. LNR introduction, a little bit about it. In summary, low energy nuclear reactions derived from a new form of nuclear process. It's produce very low levels of radiation, generally below background levels, produce nuclear fusion ash, which means that it's an actual nuclear fusion process, are not explainable through standard chemical processes. People have documented transmutation of elements. That's where one element changes into another element. That's very typical of a true nuclear reaction. It has been replicated in many laboratories around the world. It has a large volume of peer-reviewed published papers. It has no unifying theory, unfortunately, which causes all the scientists to scratch their heads and argue with one another. But it is really seriously, it is taken really seriously. A number of highly respected academic institutions and corporations, including NASA, JPL, and MIT. For those who don't know, JPL is NASA's Jet Propulsion Laboratory, and MIT is Massachusetts Institute of Technology. So here's some information. This is a clip or an extract from a paper that was declassified in 2009 from the US Defense Intelligence Agency. So it states scientists worldwide have been quietly investigating low energy nuclear reactions, LNR, for the past 20 years. So consider that that's 10 years ago. Researchers in this controversial field are now claiming paradigm shifting results, including generation of large amounts of excess heat, nuclear activity, and transmutation of elements. Although no current theory exists to explain all the reported phenomena, some scientists now believe quantum-level nuclear reactions may be occurring. DIA assesses with high confidence that if LNR can produce nuclear origin energy at room temperatures, this disruptive technology could revolutionize energy production and storage, since nuclear reactions release millions of times more energy per unit mass than do any known chemical fuel. So chemical fuels would include fossil fuels. Here's another one out of the US Defense Analysis Report. Although no one theory currently exists to explain all the observed LNR phenomena, some scientists now believe these nuclear reactions may be small-scale deuterium fusion occurring in a palladium metal lattice. This body of research has produced evidence that nuclear reactions may be occurring under conditions not previously believed possible. So that is where everybody goes, well, the only way is through hot fusion, where you actually fuse protons together in immense temperature and pressure environments like what happens in the sun. Now here's another one from a paper that was released by Mosier and Boss, investigative. So they have done an extremely thorough investigation. Stanislaus Spack, I assume is how it's pronounced, was aware of the Fleischmann-Pons experiment prior to the press conference and knew about the long incubation times. So the initial people that tried to actually replicate Fleischmann and Pons, who in 1989 released their information in relation to cold fusion, or what's known as LNR now, these people who tried to replicate it did not process their systems. They didn't allow them to incubate long enough. So there's a charging time that is required. But I'm not going to go into the technicalities of this. I'll just give you a little bit more information. So this is a paper that was released by Dr. Michael McCubre. He used to be with SRI, Stanford Research Institution, SRI. And so he asked the question, why do doubts still exist in the broader scientific community? So I'll highlight some of his words. First, there was a difficult birth in conditions that, while not initially hostile, rapidly became so. Second, there has been a great deal of poor communication on both sides and an inability to broadcast real scientific progress uncoupled from emotion or ambition. Almost complete lack of willingness on the part of those outside of the CMNS community to delve into the work and understand what has been done. And then a very, very important point, insufficiency of funding. This, nobody can actually even approach or try to really do the research needed if there is no proper funding. So this is a list of well-known US institutions which has done research in the field of LNR and also released papers. Some of them even now offer courses on this topic. So we'll go Cambridge University, Bates College, Dixie State, Department of Energy, National Security Technology, Sandia National Laboratory, the DOE in Washington, Global Energy Corporation, Jet Energy, and we can go down. So MIT, NASA, Johnson Space Flight Center, Naval Surface Warfare Center, Naval Air Warfare Center, Office of Naval Research, Purdue University, SPAWAR Pacific, SPAWAR SSC, SRI International. You remember I mentioned Mike McCubre earlier. So he worked with SRI, Texas A&M, and so on. So a very renowned bunch of people. There are a lot more institutions in Japan and Korea and all over the place, but I thought that this might be enough evidence for now. So I have in my possession, can present literally thousands of pieces of evidence. LNR is real and feasible. What is needed is urgent funding into the LNR research stream, as well as other new energy technologies, which I will um, address in another video. So it is the duty of every human whom are able to contribute, as well as the responsibility of governments to support it. Time is running out fast, people. We need to do something because, as I shown to you, current renewable technologies will not even come close to provide the base energy needs of these emerging economies while supporting current stable and mature economies. So as a last piece of evidence, I would like to present a US patent which was filed in 2013 by a very well-known international company, and it is ST Microelectronics. They do a lot of silicon chips and electronic components. So you can see here, reactor for energy generation through low energy nuclear reactions, LNR, between hydrogen and transition metals. You can go and look this patent up if you wish. There are also ones that was filed by the US Department of Defense. And what is quite important to note is up until about around I think 2010, maybe a little bit later than that, 2012, the US Patent Office refused to actually issue patents on LNR. They obviously were presented with enough evidence that allowed them to change their mind. So, thank you very much. And this was Open Conversation with Gideon Jacobs. If you found this information valuable and educational, please share it. Hit the like button on the bottom and subscribe. And thank you again for your time.